Now, the second acid-base definition system that we talked about is the Bronsted-Lowry acid-base. And so this is what we will sort of functionally use to talk about acid-base chemical reactions, right? This is how we'll try to understand them in a more detailed way. And when we go to do equilibrium problems, we will utilize this Bronsted theory to sort of the basic theoretical background of how we look at these reactions. Now, one of the big reasons why Bronsted was used, right, is it provides a much more widely applicable definition of acids and bases. So it pulls all of those bases that I said were excluded from the Arrhenius definition into the family of bases. Now, it should be understood that all reactions that were acid-base reactions or acids and bases under the Arrhenius system are also Bronsted acids and bases, but the Bronsted theory is more inclusive and it pulls these other bases into the family because they do function as bases, right? If you put them in water, they produce hydroxide. Whether we're talking about carbonates and bicarbonates or nitrogen bases, but they don't directly have a hydroxide ion in them, and so they were not part of the Arrhenius definition. But they meet the Arrhenius definition in the sense of what they do when they're dissolved in water. And so they were brought into the family of bases under this Bronsted-Lowry theory, because this is how we can understand how they produce the hydroxide ion. Now, the way Bronsted-Lowry looks at things, again, as an H plus or proton transfer reaction. And so we have the acid, which is the proton donor, right, as the source of the proton. And we have the Bronsted base as the acceptor of the proton. Okay? So it's a transfer. So we have a transfer of an H plus from one molecule to another. Right? And any reaction that involves this transfer is a Bronsted acid-base reaction. And so this is how we can, pull in these other compounds because they involve these proton transfer reactions. So again, to summarize the definitions, right? The acid is the donor, the base is the acceptor. Now, so of course the acid must contain a hydrogen, right? It can't donate an H plus unless it has a hydrogen on an atom. Now the base, if we think back to Lewis structure, right, must have an unshared pair of electrons somewhere, right? So oftentimes this means that we'll have an oxygen or a nitrogen or some other atom that has a lone pair of electrons that will accept this H plus, because you need this unshared pair of electrons to accept that H plus. And so if we think about it, this is kind of what's happening. We have our acid here, right? We have our hydrogen as part of our acid. That hydrogen is going to be lost or donated to our base, which is going to have this lone pair of electrons. So we think of the H plus moving from the acid to the base. And what we're left with, right, is a negative ion and a positive ion, which is the base plus an extra H plus, right? So the acid loses a positive charge and leaves a negative ion behind. The base gains a positive charge and generates a positive ion with an extra hydrogen, of course. And so this is a Bronsted-Lowry reaction. So, as I said, any compound that has an H plus, or has an H, could potentially be an acid. Now, not all compounds will functionally act as acids because they have to be willing to donate it, right? So because of the structure, right, a lot of times a molecule might have one hydrogen that will function as a Bronsted acid or can be donated to something else, but other hydrogens that don't. Right? And so this goes back to, we were talking about those carboxylic acids, right? And we oftentimes had different kinds of hydrogens, and we write the ones that are, quote, acidic in the beginning, and there's typically other hydrogens that aren't acidic or don't get transferred or can't get transferred other places in the molecule. So let's look at a typical acid and how we might look at it in terms of the Bronsted-Lowry definition. And so HCl, clearly an acid, and so it should function as a proton donor. So if it loses an H+, right, what's going to be left, right, is the chloride ion. Right? So HCl loses an H+ ion and leaves behind a chloride ion, right? So this would be our, as in our previous example, our A-. Right? We lost a hydrogen and a positive charge, leaving just the chlorine and now a net negative charge. Now, there has to be something to accept it, right? And so one thing that's kind of unique about different way to think about it with the Bronsted is that there is always an acid and a base in a reaction, even if it's not a, quote, neutralization reaction like we talk about with Arrhenius, because if we think about it as a transfer or a donation, then something has to accept. And so there is always an acid and a base in a Bronsted viewpoint. And so in this case, the water functions as the base, the acceptor, and as the water accepts an H+, it forms hydronium ion. So we have water that has now gained an extra hydrogen and, of course, has gained a positive charge. And so this is sort of a typical way that we look at a Bronsted reaction with an acid, right? So if we put an acid in water, this is how we would think about it from a Bronsted-Lowry point of view, as opposed to an Arrhenius view, right? Where we simply think of it as breaking up into the ions. Now, functionally, it's doing the same thing, because I could just as easily write this reaction as HCl plus water, right? We know this is going to break apart into hydrogen, but we know that hydrogen actually exists as hydronium. And then, of course, we also get the chloride ions. So functionally, what I want you to, get out of this is that we're not talking about different chemistry. I mean, when HCl goes into water, this is what it does. It forms hydronium ion and chloride ion. It's just how we look at it. The Arrhenius looks at it as simply a generation of hydrogen, which becomes hydronium ion in solution. And Bronsted looks at it as this proton transfer. So we get something that's donating a proton, something that's accepting a proton. Now, let's think about it from the terms of putting a base into water. like ammonia. And as I said before, any material that has a lone pair can potentially be a base, right? It could accept that H+. Now, oftentimes there may be more than one atom that has a lone pair, and there will be a particular one that is more willing to accept that H+, and so that's where it happens to go. So if we look at a simple base, like ammonia, right? Again, one of those bases that was not included under the Arrhenius definition, if we put it into water, right, the ammonia is a base, and so it is going to accept an H+. Now, what's it going to accept it from? Well, in this case, it's going to accept it from water. Right? Water will function in this reaction as our proton donor, and what we end up with is the base takes on that extra proton again and becomes, in this case, NH4+. The acid loses an H+ and becomes OH- or hydroxide. So here we can see how ammonia, right, one of these nitrogen bases, satisfies the requirement of producing hydroxide in water. Right? So it functionally acts as an Arrhenius base. It just was not included in the original definitions because of the structural restrictions. Now, in these two slides, we've seen water functioning as an acid here and functioning as a base when it interacts with a basic, an acid compound. Now, this is not usual, right? There's not a lot of materials that can function both as an acid and a base. These are what are known as amphoteric materials, or amphoteric substances, and they can act as either a Bronsted acid or a Bronsted base because they have both a transferable hydrogen, a hydrogen that can be lost as H+, and they have an atom with a lone pair that is ready to accept an H+. And we can see, we've seen these two reactions, an example of where it functions as a base and where it functions as an acid. So amphoteric. Now, one of the other reasons why Bronsted, besides being more inclusive, is that it gives us a nice way to think about reversible reactions. Because if we think about it as a transfer, then we have the ability to transfer back, right? If we can transfer in one direction, potentially we can transfer in the other. And so if we take our acid plus our base, right, where we're getting the H+ transfer here from our acid to our base to generate the A- ion and the HB, right? Well, we could just as easily think about the reaction going in this direction where what was formed from the base transfers an H+ back to what was formed from the acid. So now this is our acid and this is our base, and we generate what was our reactants again. So this gives us a nice way to look at reversible reactions in terms of their acid-base characteristic. Now, this also sets up pairs, right? Whoops. So if we look at this material here and this material here, these are a pair, right? It starts as this and becomes this. If we look at our base and this product, right, this becomes a pair, right? This is the base and this is what it becomes. Now, we have names for this. These are what we call conjugate pairs. And so we have our acid. We have our acid, and the acids, when we form it, this is called the conjugate base. And we have our base, and what it goes to is called the conjugate acid. And these names come from the fact that if we think about the reverse reaction, my conjugate base is now my base, right? And my conjugate acid is now my acid. And they go back to form their partner. So A gains the H plus, now the A minus is functioning as a base, gains an H plus to go back to our original acid, and our conjugate our conjugate acid of our original base reacts to go back to form the original base. So we have these pairs, right? What we call acid-base pairs. And this is how we sort of characterize them, right? So we have the original base and the original acid becoming the opposite type of species as the product. So the original base turns into an acid. The original acid turns into something that can function as a base. So our original acid, in this case water, goes into hydroxide ion, which can function as a base. Ammonia, original base, goes into ammonium ion, which could now function as an acid, right? It can give that proton back to ammonia or something. It can lose that, donate it to something else to go back to form ammonia. So these pairs can go back and forth depending on the reaction that we're looking at. And so when we go to identify them, right, we can identify the acid and the base based on what they're doing, and then whatever they become, right, that is their conjugate. So the base turns into the conjugate acid, the acid turns into the conjugate base. And so something that we need to be, conversant and are familiar with is talking about these conjugate acid-base pairs when we start to really look at reactions. All right, so we're going to stop talking about our definitions at this point, and we're going to sort of shift gears, and in the next video we'll talk about acid strength.